So let us continue. So we will have a look, as promised, on the arrays, and this is a new data type, the so-called arrays. And arrays are basically nothing else than multi-dimensional storage of elements of the same type. So basically, if you think about a matrix, which is consisting of numbers, a matrix would be an array because you have basically a collection of elements of exactly the same type. And this is the arrays are something important we will use a lot. What is the difference between lists and arrays? If you remember, if you want to define a list, then you can, of course, make the list having the same type of elements, but nothing prevents you, for example, to have also completely different type of elements within a list, or even have a list within the lists, and so on and so on. Arrays, on the other hand, always contains, or usually contains, elements of exactly the same type. That means they're a little bit more restrictive than lists. On the other hand, dealing with them, especially if they contain numbers, is much more efficient than with lists, because the computer exactly knows how many elements and what kind of elements and what type of elements these things contain. How can we use the arrays? We can use it exactly. They are defined in the NumPy package. And just to remind you, if you want to, let's maybe make a new notebook. So I will just make a new Python free notebook so that we just start with a completely empty Python session, and I will call this Python. This is lecture 04B. This is the B part of this lecture. And then in order to get access to the arrays, you would have to import NumPy. And in order to abbreviate the notation, let's import NumPy as NP. And if you want to define an array, as shown here in the slide, you just basically use np.array, and then you are listing the elements which you want to put into the array. If you already know what should go into the array, so basically if I want to define an array with the element 1, 2, 3, then I can just provide a list 1, 2, 3. Talking about matrices, matrices can be multidimensional, not just one-dimensional, which would be vectors, but also multidimensional. Of course, it's very easy to define multidimensional arrays in NumPy, and then basically you would define them. If you want to give them a value at the when you create them, then you would just pass this value as a list of lists. So let's define another array. I would call it B, and then I would just pass a list of lists. The first list would be 1, 2, 3, and the second list would be 3, 4, and 5. And if you just basically have a look at B, then it's an array which basically a matrix, a rectangular matrix with that as a first row and that as a second row. Of course, similar to matrices as you know them, of course the lines must be aligned, so basically every line must have the same length. So basically it must contain the same number of elements, and this is true even also if you have a multidimensional, more than two-dimensional matrix. Also along every index, the strips have always the same size. As discussed already, we will use them for numerical calculations because they are very highly optimized, and therefore much faster than using lists. How can I access the elements of the arrays? I can use the list notation. For example, if I had the array A, and this is containing of the elements 1, 2, and 3, if I want to access the first element, which in Python first means the second because we are starting counting by 0, then A1 is just the element 2. And similar as we have learned before, I can also modify, similar to lists, I can modify arrays. So if I want to set the first element to -1 and have a look at A, then you see that basically indeed the 2 has been changed into -1, so that has been accordingly modified. Now let's have a look on the multidimensional array, which was B, which has basically 2 rows and 3 columns. So basically if I want to have the first element of B, you can consider that's a list of lists. The first element from B would be here the second list because it contains of 2 lists, and that would be exactly the array containing the elements 4, 5, 6. And if I want within this line select an element, let's say also the first, which would be of course the second in Python, then you can write it this way. And what does it mean? You go to the first line, 0 line, first line, and the first element, 0 element, first element, which is 5. However, this way of writing is not very efficient, and you should always use, if you want to access elements in array, use the array notation, which means you are basically writing the indices here, separated by a comma, and you see you get exactly the same element, but the notation is much easier to read, and it's also much faster to manipulate those things by this kind of indexing. Everything which we have learned about lists also works with arrays, so you can have stripes, slices along, and in contrast to lists, with array you can have slices along arbitrary dimensions. And here let's redefine B as a 3 by 3 array. So basically I will just make 1, 2, 3 is the first element, and the second element is again in the list 5, 6, and the third element is 7, 8, and 9. And now if you have a look at B, we have a 3 by 3 matrix with that the first row, second row, and third row, and first column, second column, third column. And basically whatever we learned for lists, we can do it indexing things in B. However, I can do it for every index separately if I want. So for example, the first example which we hear on the slide, I would like to have B0 and then here an arbitrary range. What does it mean? Give me the 0th element of B, the 0th row, which is this one, and then arbitrary range would be all elements within. So 0, and then here the column means, okay, everything in the first row. Of course, that's the same as if you had written just B0. It doesn't make any difference. However, with that notation, you can also get the first column very, very straightforward. So you would say B and then give me all elements, so all rows within the 0th column. And then you get basically the array which contains the elements 1, 4, and 7. So that's already shows the power how you can select things. And of course, whatever we learned about indexing of lists, you can do here. So of course, you can have here a range. You could say I want only to have the first 2 rows from 0 to 2, and then the 0th column. That means, okay, column 0 is here, and then first row, first 2 rows is 1 and 4. Or I could go from the 0th to the end, but in steps of 2. Then I would get, of course, 1, then here this is will not counted, and the next one again. So in steps of 2, then I would get 1 and 7. So basically all the ranges, as we learned for this, you can apply also for arrays, and you can even select, you can even specify ranges for both indices if you want. You could say here I want to go from 0 to 2 in steps of 2, and here I want to go to 1 to 3. And what would I get for the rows? I get the 0th row and the second row because I'm jumping in steps of 2. And for the columns, I get only the first 2 because the upper index is never included. So only this and this, and therefore, for the first to the third, first is this and this. Those are the 2 because we are starting to count the columns by 0, and you see I get just 2 and 3, and then 8 and 9. So basically this is a very, very, very powerful technique, and with that you can index parts of the array if you want, and as a result you get an array which has the reduced number of elements. One thing I would like to mention here is how are the elements stored in memory. The memory of the computer is always linear, so basically the elements have a certain address, and the address is just increased by the number of bytes a certain element contains. So basically when we are here storing the element B, the array B, in the memory we have all the numbers which we stored, 1, 2, 3, 4, 5, 6, and so on and so on. And the order how Python stores them in memory, that basically the 0, 0 element is stored first, and then 0, 1, then the 0, 2, and if the first row or the 0th row has been completely stored, it goes to the next one. So basically, as you specified as a list of lists, this is exactly how it's how it will be arranged in the memory. Sometimes you are interacting with another kind of you need another kind of storage. where you go the other way around. So basically you are storing first 1, then 4, then 7, and when you finish that you could store 2 and 5 and 8. The original how is it stored is a so-called row major storing, because the row index is the one which increases slower. So basically first you increase the second index to store them and then the first one. If you go along the columns, then it's a so-called column major storing. And the only reason why you should do that if you have ever have to deal with or exchange data with programs which use the other kind of convention, typically Fortran programs are using this other kind of program convention. In NumPy it's, you can at the creation tell how the order of the array should be when you store it, and if you don't specify anything it will be the C ordering, but you can also say order is equal F, and then it would be the Fortran ordering. The nice thing is you don't see the details, so basically in the way how you access the array doesn't make any difference, but the ordering in the memory would be faster. And if it ever gets very critical for you how fast you can access your arrays in memory, then you should remember that again, because basically we can fast access the elements in the memory if the elements which we access subsequently are very close to each other in memory. So if you have a very, very big array, then going from the first row to the second row could be a very big jump in memory if the first row is very, very long, if the rows are very, very, very long. And this is something maybe you should keep in mind, and this is something you should keep in mind how you design your arrays. So you should always design your arrays that the elements you are usually accessing in an algorithm, in a loop, they should be close to each other. Okay, because then they can be reside in a cache of the processor, which is very, very fast. Okay, so once you have the array, you can query, for example, the size and the shape. The size of B is just the number of elements, which would be 9. The shape of B is B.shape is basically just a tuple which gives you the number of elements along the first index and second index along the, if it's a 2-dimensional, then you can interpret this along the row and the columns, so how many rows and how many columns this matrix has. You can even change the shape if you want, actually. So if you think about B, if you look at B was 3 by 3. I can also say that B shape should be, instead of one row and 9 columns. And if you just overwrite that, then it turns out it doesn't work because I was storing it as a Fortran array, and that doesn't work. So let's basically here remove this order equal F and do it again. And then now let's have a look. B.shape is again 3 by 3, and now I can just reshape it. And if I now print B.shape, then it would be 1 times 9, and if I print B, it would be just the elements. Basically here it's an array which has only one row and 9 columns. And what is the order of the elements? Exactly, the order of the elements is the one how they are in the memory. And because here we did not specify the order equal F, they are stored in memory exactly in the way row-wise. So basically first the columns of the first row are stored and the columns of the second row, and so on and so on. And this is exactly the order which you get here. I could also override the shape and make basically a vector of that which has 9 rows but only one column, and then the parentheses I can leave away because it's not ambiguous here. And if I look at B, it's exactly then a column vector. If I try to reshape B to something which has a different number of elements, I try to change the size, let's say 2 times 4, then it doesn't work because it has 9 elements, so it cannot be casted into a shape of 2 times 4. So, but the reshaping is very easy. Arrays are mutable as we discussed, so we can override basically any element, as we have seen, without any problems. Again, you should not forget that arrays are mutable object, and that means all the kind of side effects you have in Python for mutable objects is also true for arrays. So if we just remember our array A, which was we had the element 1, -1, and 3, let's just set it back to the original value. to the 1, 2, 3, and this we just make an array out of that, a numerical array with those elements. And then let's say that the array B should be just A. Then we have exactly the same effect. Okay, A has the right value, B has the right value, and if I know changing the, let's say, the second element in A, which would be the last element, to -3 instead of 3, then A has been changed, but unfortunately also B has changed. And the reason again for that is, as you remember here, just remember that picture here, that basically if you create an array, you basically create an object in the memory, and then if you say B is equal A, you just give two names which are pointing to the same object in memory. And now we know the operator, we can also check A is B, whether A is B and true, which means they are showing to the same object in memory. Again, if you do not want to make sure that it does not happen, then you have to copy the array, and the array can be copied just by basically just saying mp array and then give it array, and then you make a copy. And now if we look at A and B, they have both the same original values. Sorry, I should also redefine A. So I'm redefining A and then B, and then A and B, they have both the values 1, 2, 3. But because I made here a copy, a true copy, therefore they are pointing to different objects in memory. So now if I'm changing the value of A2, then it's indeed changed, but B is not affected because it's something different in memory, different object, and also A is B would give me false, so they are two different objects. So basically this basically works exactly as lists. Also, if you cut out parts of an array with the range, so just let's say A, this is the array 1, 2, -3, and then now I say B should be the same as A and just the first two elements. Okay, so A is this way and B is this way. And again, if I'm modifying A, so as I set the 0 element to -1, then basically B, which was just a view, which was a slide out of this array, it also changes. So basically, do not forget, if you are just taking here as here, you are just taking a slice of an array, then what you get back is basically not a new array, but just a view which points to the same data as before. So if the data changes, also your view changes. And again, if you want to make sure that it is independent, then basically what you would have to do is here, instead of saying B is equal A 0 to 2, you can just pack it in the array function, right? So basically you are making a copy of that, and then here you see A and B, those are -1, 2, the first two elements. But now if we change back the element of A to the original value 1, then B is still unchanged. Let's see whether A is changed. A has been changed back, but B is unchanged because we now made a copy of this area. Okay, so again, the only thing, it's very logical and very consistent, because arrays are just mutable objects. But remember, if your mutable objects means if you're just making an assignment, or with the arrays, if you are getting out a slice of the arrays, it always points to the original data in the memory. And if you don't want to do that, you have to make explicit a copy out of that. You can do with arrays exactly the same arithmetic operations than with scalar. The rule is, even whenever you do something, it's always done element-wise. So let's say here we just take the example from the slides. So we have an array with the element 1, 2, 3, and another element B with the element mp.array, and then it was 5, 4, and 3. So here I have A, here I have B. Now, for example, I could add up the two arrays. What would I get? It would be added element-wise, so that with that, this element with this element, and this element with this element. And then I get an array with 3 elements, which all contains the sum of the corresponding elements in the original arrays. Of course, the shape of the arrays must be the same. So if I try to add to A another array, which has only 2 elements, then of course this won't work. Of course, not just addition, multiplication also works. Again, this works element-wise. 1 times 5, 2 times 4, 3 by 3. Also, comparison works usually element-wise. If you say A equal B, whether A is equal B, then you get an array which for each element-wise compares. Is the first element the same as the first element here? Is the second element the same as the second here? The third as here? And for each of them, you get the corresponding logical. It even says, okay, I have now an array with the data type of bool, so basically an array containing logicals, and so on and so on. One thing I would like to mention, this is a little bit advanced topic, but it's nevertheless, it's very, very useful if you are doing arithmetics or things with arrays, is a so-called broadcasting. I just explained you that arrays must be always have the same shape if you want to multiply them or add them, but it's not always true. And here the example I would like to make, the same example as on the slide. So let's first create a 2-dimensional array 1, 2, 3 with a second row of 4, 5, 6. That's my A, and my array B should be the array -2, -3, -4, for example. Now the question is, can I, for example, multiply the 2 arrays together? And in theory, I cannot. Why? Because this array has the shape, we can also query it, the shape of array A is 2 by 3, while the shape of B is just 3. And exactly this is actually the reason, this special shape of the 2, that I can combine them, because the last indices are fine. So basically, if your shape is such that the last or a few of the last indexes are, so if you are starting from backwards on the shape, that the indexes are the same, then you combine the 2 arrays with each other. So let's try first, just before we have tried to understand what happens. I can multiply A times B. And what kind of shape do I get? I got the same shape as I had for A at the beginning. So A times B had the same shape as A had. And what happened? Basically, what happened is that NumPy was taking this array B and it was repeating it in a way that it gets the same shape as A has. And if you look at the slide, it's even shown how you can do that. You had just basically a vector B, which had only the shape 3, and in order to make from that something which has this shape 2 times 3, you have to repeat it along. So basically, if you consider them as a row, you have to repeat them and make subsequent rows, and then you get an array which has the same shape as A, and you can multiply it. Actually, I could have done it also differently. I could have and I want just to show you that, I could have created an array C np.array, which consists of the array B and once more the array B, and then A times C would have been exactly the same. You see? So basically, we are not doing as just repeating the array B as in an array. And that works automatically as long as the shapes are compatible, such that if you start from the backwards and the reverse, then the indices are matching, and up to the point basically from the smaller, all the indexes must match, and then the indices which remain, like the 2 here, the array will be repeated accordingly. But sometimes we want to do it the other ways around. I would like to now have something where I want to multiply the first elements in the first row by 1 number and the elements in the second row with a different number. So this is my array A, and I would like to multiply every element in the first row by -1 and every element in the second row by -2. So I will just make an array, let's say D, and that would be the array -1 and -2. The problem is, if I try now to multiply A and D with each other, that doesn't work. Why? Because they cannot be broadcasted together. Why? Because if you look at the shape of A, it's still 2 by 3, but if you look at the shape of D, you see that is 2. So they are matching now from the beginning, but not from the end. So if you go reverse, then they are not matching. And somehow I would like to signalize NumPy that I want to have a matching for the first, basically for the first index. And then here I would like to insert here a second index to make sure that D has the right shape, and that I can do by basically using the so-called new axis construct. And I can say that A multiplied by D, and then I am inserting here I take everything from the first index, and the second index is missing, but I want to have new numpy to repeat D so that the second index is also existent, and then I can indeed achieve what I want. If you look at the figure here, you see what happens. I had again the array 1, 2, 3, 4, 5, 6, so 2 rows and 3 columns each row. And basically what numpy did is now take the vector -1, -2, and it was repeating it along the second index. That means that it was considering the vector as if it was a column vector, and then basically repeating along the column index. And that means this is new axis, exactly what it tells you. It tells you, okay, repeat the array along this index. While if you don't specify anything, then it repeats also only along the first indices. Therefore, the arrays must match. The last indices must match. But with the new axis, you can just reverse that, and then it's you can make a case where the first indices match, and then the array is repeated along the second index. So it's just that you remember that if you are working with arrays and something happens which you don't understand, especially if you are multiplying arrays which seems to be shape incompatible, but NumPy does it, then you know this is because of the broadcasting, and then this way you can also enforce broadcasting if needed. Okay, also we can apply functions on the arrays. Those are universal functions, and again, it's maybe not that very surprising. This is done element-wise. So let's, for example, define an array, numpy.array, and then I would just give it the value or let's do it 0, then numpy.py, numpy, so the numpy module has also the constant pi, which is just basically the value of pi. Then let's take mp.py and 3 times mp.py, for example. And then also it contains the sinus function, the numpy module also, and if I just take sinus of a, then I get exactly 0, 1. I was messing it up. I wanted to have 3 pi over 2.0, and then it's all setting as 0, 1, 0, -1 basically, right? So basically those things are applied element-wise, and there are a lot of useful functions in NumPy, like the square root functions, like the trigonometrical functions, or rounding functions as floor on sale, which gives you, floor gives you basically the integer below that, the sale, the integer above that. Basically this is something you can look up in the documentation of the NumPy if you ever need that. There are also functions to reduce the array, which means basically contract the array into one number, for example, by summing up all the elements. And if I just make an array which should have the value 1, 2, 3, and if I wanted to calculate the length of this vector, for example, then I could first just take the second power of a, which means element-wise it would take the power of every element separately. So here 1, 4, and 9. And now I could just take the np.sum function, which would just sum up those values, which would be 14, of course. And if I wanted to have the length, then I need the square root of that, which is also present in the NumPy package, and then that would be the length of this array. So those are the reduction functions. The most important are sum and product, of course, if you want to multiply the elements with each other, or sum if you want to just sum them up. We can also do matrix multiplication. So arrays are a little bit like matrices, and you can do matrix multiplication, of course. And if we just define our, let's say, array, let's call it A again, with just 1, 2, and 3 and 4, and our array B as 5 and 6. Then I have here a 2 by 2 array, which I can multiply, of course, by a vector which has two elements. And the matrix multiplication, there are two different ways you can do that. You can do it either with the dot function or the matmul function, right? So you can say mp.dot e times b, and then you get, of course, here this matrix times this vector. So this vector will be then interpreted as a column vector. So you have here a 2 by 2 matrix multiplied by 5, 6 as a column vector. If you can also say np matmul, so matrix multiply a and b, and you will see that you get the same. And if you have a recent Python 3.5 or above, you can even say a and add b, and then you get the same. So basically you don't have to use a function, you can use the add operator, which is associated with the matrix multiplication. The only thing you should be aware that dot and matmul are not 100% equivalent. If you have arrays which have more than 2 indices, so 3, 4, 5 and above, then they behave a little bit differently, and basically the add operator behaves exactly as matmul. So it's a matrix multiplication, while the dot function behaves differently. So if you are manipulating arrays which have more than 2 indices, then please consult the manual and make sure that you understand whether you need matrix multiply or dot. Okay, and then basically what we want to do is to how you can create arrays. So basically until now we created arrays by basically specifying their values explicitly. But this is not always the case. So basically we said mp.array, and then we said okay 1, 2, 3, and then we got just an array with 1, 2, 3. Of course it could be that you specify them as integer, but you want nevertheless to make sure that Python knows that it's a float array. Why would you want to have this way? Because if you want specified an array, then the type of the array cannot be changed. So it's all fine, a is 1, 2, 3, but what happens if I now override the 0th element of a with a floating point number, minus 1 point, let's take minus, sorry, let's take 1.2, and now if you look at a here, so then you see that it was only minus 1. Why? Because the type of the array was set here to an integer. That means whatever you put into the array will be converted to an integer. But at the creation, I can already type it should be just a float. And then you see, okay, the difference is that now I have floating point numbers instead inside. And then if I set it to something else, it will be not run it on integer, but it will be treated as a float. So basically, you can set the type of the array at the when you create it with the dtype option. And that's also very handy if you want to, for example, create an array with zeros. Also, then with zeros, you also have to specify this, the shape. And then with the dtype, you are saying that you would like to have a float array, and then you get here a 3 by 3 0 array. If you want to fill it up with ones, that's also possible. There's the function ones, then you get to have 1 everywhere. And the nice thing is if you want to fill it up with something like 20, the value 20, then of course the only thing you have to do is multiply it with 20. Multiplication with a scalar will be done element wise, so basically every element of the array would be multiplied by this number 20. Okay, and maybe last but not least, one interesting thing is the empty array. If you want to create an array which you will fill up later step by step, and you don't want to associate any value with the numbers because you will anyway fill up all the numbers later, you can also specify, let's say, an empty array. Let's make it 2 by the shape 2 by 3, and the data type should be float. And if you look at that, it basically contains some kind of numbers. Here they are 0, but they do not have necessarily to be 0. It can be any arbitrary number. It just say create an array, and I'm not don't care about the content so far. I will fill it up later, step by step. Okay, good. And basically the last thing I would like to treat as when finishing this session is how you can iterate over arrays. Arrays are like lists, as we have seen at the beginning, and indeed also for iterations they are treated as lists or lists of lists if they are multidimensional. So basically if you're writing a loop, it will be behave exactly the same way as if it were a list. So for example, if you have a one-dimensional array which is just called a vector, then this vector, basically it's something like a list. And basically if you have a look at a for construct here, a for loop, then you can say for some element in vector, and then we just print it out. So we are not doing anything really useful here, but you see that it will run over the elements, and it will print 1 and then 2 and then 3, because basically that's like if it were a list. Now let's have a look what happens if you have a multidimensional array. Then if you have an MP, let's say A is a, or maybe A is still there. No, what about B? Okay, and let's just define it. So I need a multidimensional array 1, 2, 3, and then 4, 5, 6. So my A is now a multidimensional array, and if I would make an iteration over that, then it's a list of lists. That means the first element in the iteration would be this list or this array. The second element in the iteration would be this element, so this list or this array. So basically I would iterate over the rows of the array. So basically for row in A, print row, and I will just write also the word row in front, that we see that it belongs to a different iteration, and then you see exactly it will iterate over the rows. So basically in terms of iteration in for constructs, arrays are behaving exactly as they were the corresponding lists of lists. So it's quite consistent. With that, I would like to finish our session on the arrays and how to deal with them with Python. You can look at the NumPy documentation for further routines. We will get now a few more NumPy routines during this course, but of course we will definitely not cover all of those routines. So whenever you need something look up before you code it by hand, please look up in the NumPy routines whether there are appropriate routines for that, or in the SciPy routines whether they are already appropriate and maybe much faster implementation than what you would set up. If they already exist, you should use that. With that, I would like to thank for your attention. Please do the exercises so that you get you get this notation and this array manipulating well trained, because this is something which will be used a lot in the next sessions. Thanks a lot for your attention, and take care.